Welcome to this exploration of time and quantum gravity. Let your mind settle as we journey through some of the deepest questions in physics. There's no need to rush, simply listen and let these ideas wash over you like gentle waves. We begin at the heart of a profound mystery. Imagine two great theories of the universe, standing side by side, each describing reality with breathtaking precision. Yet when we look closely, we find they speak different languages about something as fundamental as time itself. In quantum mechanics, time flows uniformly, absolutely, like a river that never changes its course. It is the stage upon which quantum events unfold, always moving forward at the same steady pace. But in general relativity, Einstein's theory of gravity, time is something altogether different. Here, time bends and stretches. It is woven into the very fabric of space-time, curving around massive objects, slowing down in deep gravitational wells. This creates what physicists call the problem of time. How can time be both absolute and dynamical? How can it be both a fixed stage and a flexible participant in the cosmic dance? When we try to merge these two great theories into a quantum theory of gravity, something remarkable happens. The equations seem to suggest that the universe itself might be frozen, with no conventional evolution at all. Time, as we know it, appears to vanish from the deepest level of reality. Take a moment to consider this. The flow of time that feels so real, so undeniable in your experience right now, might not exist at the most fundamental level of the cosmos. This strange timelessness becomes mathematical reality in an equation called the Wheeler-DeWitt equation. Named after physicists John Wheeler and Bryce DeWitt, this equation attempts to describe the quantum state of the entire universe. But here's what makes it so peculiar. When you write down this equation, there is no time variable, none at all. The wave function of the universe in this formulation simply exists. It doesn't evolve, it doesn't change. It just is. Imagine trying to describe a movie without any concept of before or after, without any frames progressing forward. That's what the Wheeler-DeWitt equation asks us to do with the universe itself. It presents us with a formally timeless cosmos, a universe frozen in an eternal quantum state. This isn't a failure of the mathematics. It's a direct consequence of trying to treat the universe quantum mechanically while respecting the lessons of general relativity. But it forces us to ask uncomfortable questions. If the universe has no time at its deepest level, where does the time we experience come from? How does change emerge from changelessness? These questions have haunted physicists for decades, inspiring new ways of thinking about reality itself. Let's zoom in now, from the universe as a whole to isolated quantum systems. Even here, in the microscopic realm, we find hints of timelessness. Consider a quantum system, perfectly isolated from its environment. Perhaps a single atom, shielded from all external influences. When we examine its quantum state mathematically, we find something curious. There is no intrinsic arrow of time. The fundamental equations work just as well forward as backward. The sense of time flowing, of past giving way to present and present to future, doesn't live in the quantum state itself. Instead, it appears to be tied to other things. Measurement, entropy, interaction with the environment. When we measure a quantum system, we become entangled with it. We create correlations between ourselves and the system, between our recording devices and the quantum world. And it's in these correlations, these relationships, that temporal flow seems to emerge. Similarly, entropy, the measure of disorder, gives us an arrow of time. In isolated systems, entropy tends to increase, defining a direction from past to future. But this arrow is statistical, not fundamental. It emerges from the behavior of many particles, not from the basic laws themselves. So even in quantum mechanics, time as we experience it seems to be something that emerges, something that arises from relationships and statistics rather than being woven into the fundamental fabric. This realization leads to a beautiful idea: relational time. If time isn't fundamental, if it doesn't exist as an external absolute flow, perhaps we can define it internally. Perhaps time is something that emerges from the relationships between different parts of a quantum system. Think of it this way. Instead of asking, "What time is it?" we ask, "What is the state of this part of the system relative to that part?" Time becomes a correlation, a relationship between quantum subsystems. Imagine two quantum clocks, both part of the same isolated universe. Neither clock has access to some external cosmic time, but they can still be correlated with each other. When one clock reads noon, the other might read midnight. These correlations create a kind of internal time, a way of ordering events without reference to anything outside the system. This is time as an intrinsic, quantum observable, time that emerges from within rather than being imposed from without. It's time observed within the universe, not time as viewed by some imaginary external observer floating outside of everything. The beauty of this approach is that it takes seriously the idea that the universe is all there is. There is no outside. There is no external clock ticking away. There is only the universe and its internal structure, its internal correlations. How do we make this idea mathematically precise? Through quantum clock models. These elegant constructions show us how to recover the familiar flow of time from a fundamentally timeless framework. Here's how it works. We take part of our quantum system and designate it as a clock. Then we condition the state of the rest of the universe on the readings of this clock. We ask, when the clock reads 3 o'clock, what is the state of everything else? As the clock variable changes, the conditional state of the universe evolves. And remarkably, this evolution follows the familiar Schrödinger equation, the fundamental equation of quantum mechanics that describes how quantum states change with time. So we've done something extraordinary. We started with a timeless quantum state, with no evolution whatsoever. But by carefully choosing internal correlations, by designating part of the system as a clock, we recover temporal evolution. Time emerges from timelessness through the structure of quantum correlations. This isn't just a mathematical trick. It's a profound insight into the nature of time itself. It suggests that time is not a fundamental ingredient of reality, but rather a way that correlated quantum systems appear to one another. Let that settle in your mind. Time, the very medium through which you experience existence, might be an emergent phenomenon, arising from the quantum correlations within the universe. But perhaps time never truly disappeared. Some physicists have developed approaches that suggest the timelessness of quantum gravity might be more apparent than real. These approaches use what are called extended Hamiltonian formalisms, sophisticated mathematical frameworks that treat time more carefully. In these formulations, we can recover a genuine cosmic time, a global notion of temporal flow that applies to the quantum universe itself. The key is to enlarge the space of variables we're working with, to carefully distinguish between different notions of time, and to use the constraints of general relativity in a more subtle way. When we do this, something remarkable happens. We find that the quantum universe can indeed evolve. There is a Schrödinger-like evolution, a genuine dynamics, even at the level of quantum gravity. This doesn't contradict the Wheeler-DeWitt equation. Rather, it shows us that there are different ways to formulate quantum gravity, different mathematical languages we can use. Some make time disappear, others preserve it. The challenge is understanding which formulation corresponds to physical reality. Perhaps time was always there, hiding in the mathematical structure, waiting for us to find the right perspective to see it clearly. Now let's shift our perspective entirely, from quantum states to the structure of space-time itself. There's an approach to quantum gravity called causal set theory that takes a radically different view. In causal set theory, the fundamental ingredient of reality is not a smooth space-time continuum, not a geometric manifold, but rather a discrete set of points with causal relations between them. Some points can causally influence others, some cannot. These causal relationships form a partial order, a structure that determines which events can affect which other events. In this framework, time doesn't emerge from quantum correlations or thermodynamics. Instead, it's built into the causal structure itself. The causal order, the fact that some events must come before others, gives us a notion of temporal sequence. But it's not quite the time we're familiar with. It's a discrete, granular time built from the fundamental causal atoms of space-time. Smooth, continuous time is something that emerges only at large scales, when we average over many causal set elements. This approach treats causality, the relationship between cause and effect, as more fundamental than geometry. Space-time geometry emerges from the causal structure, not the other way around, and with it, a notion of temporal ordering emerges from discrete causal relations. Causal set theory doesn't just give us a static causal structure, it also provides a dynamics, a way for the universe to evolve. And this dynamics is unlike anything in conventional physics. In causal set dynamics, space-time doesn't exist all at once. Instead, it grows, element by element, through a fundamentally random process. Imagine the universe adding one causal set element at a time, choosing where to add it according to certain probabilistic rules. This creates a stepwise, stochastic notion of time. Time isn't smooth and continuous, it's jumpy and random. The universe takes discrete steps, and each step is probabilistic, not deterministic. There's no background continuum, no pre-existing stage on which this growth happens. The causal set simply becomes larger, one element at a time, building space-time from the ground up. This is time as creation, time as the process by which the universe brings itself into being, moment by moment. It's a radical rethinking of temporal flow, one that makes randomness and discreteness fundamental to the nature of time itself. As you contemplate this, notice the quiet between these words. In that silence, perhaps, there's a hint of the gaps between discrete moments of cosmic creation. Now we venture into even more speculative territory, to ideas inspired by holography and the relationship between quantum information and space-time. There's a profound principle in modern physics called the holographic principle, which suggests that a region of space-time can be completely described by information encoded on its boundary. The three-dimensional interior and the two-dimensional boundary are different descriptions of the same reality. But here's where it gets truly strange. We can have a timeless state on the boundary that corresponds to a dynamical, time-evolving space-time in the bulk. The boundary exists in a kind of eternal now, with no temporal evolution, yet it encodes a bulk space-time, where time flows and events unfold. How is this possible? Through entanglement. The quantum entanglement structure of the boundary state determines the geometry of the bulk spacetime, including its temporal properties. Different patterns of entanglement correspond to different spacetime geometries, different ways that time can flow. So entanglement itself, the purely quantum phenomenon of correlation between distant systems, appears capable of generating temporal geometry. Time emerges from the pattern of quantum correlations. This is time as an emergent feature of quantum information, time as a consequence of how the universe organizes its quantum data. We end this first segment with the most speculative vision of all, an idea that pushes emergence to its absolute limit. What if there is a fundamentally timeless energy substrate underlying all of reality? A realm of pure potentiality, of energy without form, existing in a state that has no temporal character whatsoever. From this substrate, everything emerges. Space-time itself, the geometry that Einstein showed us, the quantum fields that fill the vacuum, gravity, and yes, time itself. Time is not fundamental. It's not built into the base layer of reality. It's a late-stage feature, something that appears only when the universe takes on a certain level of complexity and structure. In this vision, Asking what came before the Big Bang is like asking what's north of the North Pole. The question assumes time exists fundamentally, but time itself is something that emerges, something that has a beginning not in time, but in the logical structure of emergence. This is the most radical rethinking of time possible. Time as a phenomenon that arises from a deeper, timeless reality. Time as something the universe creates rather than something the universe exists within. As we pause here, let your mind rest with these ideas. Don't try to grasp them fully. Simply let them be, like stars in the night sky, beautiful and distant and mysteriously illuminating. Welcome back to this meditative journey through the nature of time in quantum gravity. In this segment, we'll explore how different approaches to quantum gravity reveal time as an emergent phenomenon. Breathe deeply, relax, and let these ideas flow through your consciousness. We begin with a principle, a constraint that shapes much of modern quantum gravity research. Background independence. This principle states that there should be no fixed, pre-existing space-time background in our fundamental theory. Think about what this means. In ordinary physics, we assume there's a stage, a theater of space-time in which events occur. This stage has a geometry, a metric that tells us how to measure distances and durations. We take this stage for granted, treating it as a fixed backdrop. But general relativity taught us that space-time is dynamical. It curves and bends in response to matter and energy. The stage is part of the play, an actor rather than mere scenery. So why should we assume it exists beforehand? Background independence takes this lesson seriously. It says, don't assume any fixed space-time structure. Let spacetime and its geometry emerge from the fundamental theory itself. But here's the consequence. Without an external metric, without a fixed spacetime background, time cannot be assumed. There's no pre-existing cosmic clock ticking away. Time must arise from the theory's internal structure, from the relationships between the fundamental variables. This forces us to rethink time from the ground up, to find new ways of defining temporal flow without relying on an external framework. It's a challenging constraint, but also a liberating one, opening up new possibilities for understanding what time really is. One of the most developed approaches to background-independent quantum gravity is loop quantum gravity. This theory takes seriously the idea that not just matter and energy, but geometry itself should be quantized. In loop quantum gravity, we discovered that space has a discrete structure at the smallest scales. Areas and volumes come in discrete packets, quantum chunks of geometry. You can't divide space indefinitely. Eventually, you reach a fundamental limit, the Planck scale, where space itself becomes granular. This quantization of geometry has profound implications for time. If space is discrete at the Planck scale, roughly 10 to the minus 35 meters, then we should expect time to break down at the corresponding Planck timescale, about 10 to the minus 44 seconds. Below this scale, the very notion of smooth, continuous time ceases to make sense. Time might be discrete, jumping from one moment to the next with nothing in between. Or it might lose its meaning entirely, replaced by something stranger, something we don't yet have words for. The quantum nature of geometry strongly suggests that classical time, the smooth, flowing time of our everyday experience and even of Einstein's relativity, is an approximation. It works wonderfully at large scales, but fails at the universe's smallest scales, where quantum geometry reigns. Loop quantum gravity doesn't just quantize space, it also provides a picture of how quantum geometry evolves. This picture is based on mathematical objects called spin foams. To understand spin foams, we first need to understand spin networks. These are graph-like structures with nodes and edges that represent quantum states of spatial geometry. The edges carry quantum numbers that determine the areas of surfaces, and the nodes encode how different regions of space connect. But space isn't static, it changes, it evolves, so spin networks must evolve too. A spin foam is the history of a spin network, the four-dimensional structure that encodes how quantum geometry changes from one spatial slice to another. Think of it like a movie made of discrete frames. Each frame is a spin network, a snapshot of quantum space. The spin foam is the entire film, the complete history of how these snapshots connect and transform. But here's the crucial point. This evolution is defined without any background time. We don't assume some external time parameter along which the spin networks evolve. Instead, evolution is defined through sums over all possible space-time histories, all possible spin foams that connect an initial to a final configuration. This is a timeless formulation of dynamics. We don't ask, how does the system evolve with time? We ask, what is the quantum amplitude for this space-time history? Time, as a dimension in which things unfold, is part of the history, not a parameter outside it. The dynamics of spin foams are built in a very specific way. They're not based on time-dependent metrics or conventional evolution equations. Instead, they're constructed from the eigenvalues of geometric operators. In quantum mechanics, observables like position or momentum have eigenvalues, the specific values you get when you measure them. In loop quantum gravity, geometric quantities like area and volume are also observables, and they too have discrete eigenvalues. Spin foam dynamics uses these geometric eigenvalues as its building blocks. The amplitude for a particular spin foam depends on the quantum numbers labeling its edges and faces, which correspond to discrete areas and volumes. Time doesn't appear explicitly in these formulas. There's no time-dependent Schrödinger equation, no temporal evolution operator. Instead, there are transition amplitudes between quantum geometries, calculated by summing over discrete space-time histories. Only at large scales, when we coarse-grain over many Planck scale elements, does an effective, continuous space-time emerge. And with it, an emergent time dimension appears, a smooth parameter that approximates the underlying discrete reality. This is time emerging from timeless geometry, from quantum areas and volumes combining to create the illusion of smooth temporal flow. If time is not fundamental, we face a deep question. Where does it come from? We've seen several answers already. Here's another, perhaps the most elegant. Time comes from thermodynamics. This is the thermal time hypothesis, proposed by physicist Carlo Rovelli and others. The idea is simple yet profound. Equilibrium states. The state systems settle into when left alone, themselves define a flow of time. Think about thermodynamic equilibrium. At equilibrium, macroscopic properties don't change. Temperature is uniform, pressure is balanced, nothing seems to happen. Yet, microscopically, particles are still moving, still evolving according to their microscopic dynamics. The thermal time hypothesis says that this microscopic flow, the evolution of a system at equilibrium, defines time. Time is not imposed from outside. It's an intrinsic property of the thermodynamic state itself. Different states define different times. There's no universal cosmic time independent of the system's state. Time is relational, state-dependent, emergent from the thermodynamic structure of reality. This connects deeply to the idea that time's arrow, its direction from past to future, comes from entropy. If thermodynamics can give us the arrow of time, why shouldn't it also give us time itself? The thermal time hypothesis isn't just a philosophical idea. It has a precise mathematical foundation in something called modular theory, a branch of mathematics dealing with operator algebras. Here's the basic idea. In quantum mechanics, we describe physical systems using operators on a Hilbert space. These operators form an algebra, a mathematical structure with specific properties. When we specify a state on this algebra, something remarkable happens. The state itself generates a time evolution. This evolution is called modular flow. It's a natural transformation of the operator algebra that depends on the state we've chosen. Different states generate different modular flows, different notions of time evolution. For thermal equilibrium states, the modular flow coincides with time evolution in the usual thermodynamic sense. The state at temperature T generates a flow that matches what we expect from statistical mechanics. So time becomes a derived property of the system's algebraic and statistical structure. It's not put in by hand, it emerges from the mathematics of quantum states and observables. This is a beautiful unification of ideas from quantum mechanics, thermodynamics, and pure mathematics, all pointing toward the same conclusion. Time is emergent, a feature that arises from deeper, more fundamental structures. We can extend this thermal logic even further to quantum spacetime itself. What if spacetime is fundamentally a statistical ensemble, a collection of possible geometries weighted by some probability distribution? In this view, quantum gravity is inherently statistical. The universe isn't in a single definite spacetime geometry. It's in a quantum superposition of many geometries, or perhaps an ensemble of possibilities, like a statistical mechanical system with many microstates. If spacetime is statistical, then entropy becomes crucial. The entropy of quantum spacetime, the number of microscopic configurations consistent with what we observe, helps determine which geometries are most probable. And here's where time enters. The thermodynamic state, the statistical ensemble we choose, determines both the geometry and the temporal ordering. Entropy and state selection work together to define what space looks like and how time flows. This is a deeply holistic view. Geometry, time, and thermodynamics are not separate ingredients, but different aspects of a single statistical framework. You can't have one without the others. They emerge together from the quantum statistical structure of spacetime. Now we turn to a completely different approach to quantum gravity. Asymptotic safety. This program seeks to make gravity well-defined at all energy scales using the techniques of the renormalization group. In quantum field theory, we often encounter infinities. The renormalization group is a mathematical procedure for dealing with these infinities, showing how the properties of a theory change as we examine it at different energy scales. Asymptotic safety proposes that gravity too can be renormalized, that there's a way to make quantum gravity mathematically consistent at all scales. The key is a fixed point in the renormalization group flow, a special configuration where the theory becomes scale invariant at high energies. But here's what's relevant for our discussion of time. The renormalization group procedure introduces its own notion of time. As we change energy scales, as we flow from high energies to low energies, or vice versa, the effective laws of physics change. This flow defines a kind of temporal ordering, what physicists call RG time. RG time tracks how space-time physics changes with scale. At high energies, approaching the Planck scale, the effective dimensionality of space-time might change. Quantum corrections might become important, and the nature of time itself might be modified. This connects the abstract mathematical flow of the renormalization group to physical cosmological time. Perhaps the evolution of the universe, the flow of cosmic time, is related to this flow through energy scales. Renormalization group studies of quantum gravity have revealed something unexpected. Spacetime might effectively lose dimensions at ultra-high energies. This phenomenon is called dimensional reduction. As we probe smaller and smaller distances, approaching the Planck length, spacetime appears to become lower dimensional. The full 4 dimensions of spacetime, 3 of space, and 1 of time seem to melt away, leaving a 2-dimensional or even fractal structure. Different approaches to quantum gravity, including asymptotic safety, loop quantum gravity, and others, have found hints of this dimensional reduction through different calculations. The phenomenon appears to be robust, suggesting something deep about the nature of spacetime at the Planck scale. If spacetime loses dimensions at high energies, time must behave very differently in this regime. In 2 dimensions, time would be just one of 2 directions, not one of 4. In a fractal spacetime, the very notion of dimension becomes ambiguous, and time might not be a well-defined concept at all. This radically altered temporal behavior at the smallest scales reinforces a theme we've encountered throughout. Time, as we know it, is an emergent, approximate concept. At the fundamental level, something stranger is going on, something our everyday intuitions about temporal flow cannot capture. We close by emphasizing a subtle but crucial point. RG time, the parameter that tracks renormalization group flow, is not the same as the physical time we experience. RG time is an abstract mathematical parameter. It measures where we are in the space of theories, at what energy scale we're probing physics. It's a tool for organizing our understanding of how quantum field theories behave at different scales. Physical time, on the other hand, is what clocks measure. It's the parameter that appears in the Schrödinger equation, the dimension along which causality operates, the arena in which our lives unfold. Yet there are deep correlations between these two notions of time. The renormalization group flow is not arbitrary. It's constrained by physical principles, by unitarity, by causality, by thermodynamics. And in cosmology, the evolution of the universe through physical time is intimately connected to how energy scales change, how the universe cools and expands. So while RG time and physical time are different, they're not unrelated. The flow through the space of theories might be the abstract shadow of the concrete flow of cosmic time. Scale evolution might underlie temporal evolution. This hints at a profound possibility: that physical time, the time of our experience, emerges from more abstract notions of flow. Not just thermodynamic flow, not just correlational flow, but the logical flow through the space of possible physical theories. Perhaps time is the universe's way of exploring the landscape of its own possibilities, the parameter along which reality flows through the space of what could be. Let these ideas settle gently in your mind. There's no need to understand everything, no need to hold on to any particular concept. Like waves on a shore, let these thoughts arrive and depart, leaving behind a sense of wonder at the deep mystery of time. Rest now, and let the cosmos contemplate itself through your quiet awareness.